We now look at the D flip-flop, and we observe that D flip-flop can be obtained from JK flip-flop by introducing an inverter across the two inputs, and therefore it becomes a one input flip-flop. Remember that for the first two that we have discussed, that is SR and JK, they always had two inputs. But if you invert one input of JK such that they are always going to be complementary to each other, then you end up with a D flip-flop. And this is called D flip-flop because it's also starts for delay flip-flop. And we'll see why it's called delay, because the output kind of follows what is coming at the input with one clock pulse delay. So we are saying that the D flip-flop may also be obtained from the SR flip-flop, again by introducing an inverter across the inputs. So we can form a D flip-flop from either JK or D flip-flop or SR flip-flop by doing the same thing, and we end up with the same result. The characteristic table, without necessarily deriving it, is simply coming from the JK flip-flop. If you remember, we said that JK has this kind of characteristic table. So this is the characteristic table for JK, but we are saying that the two inputs to JK are complementary, and therefore we'll never have them being the same. Therefore, the 0, 0 is eliminated, and the 1, 1 are eliminated, because we are saying that when J is 1, the K is inverted, and therefore we get a 0. So those two possibilities are removed from the table. Therefore, we are only left with the other two, and therefore we are saying J is going to be equals to D, and the other input of J is inverted, and therefore we are able to get this is the truth table or the characteristic table. And therefore, when J or D is 0, the next state becomes 0, and when D is 1, the next state becomes 1. That is what we say is called a delay flip-flop, meaning that the next state will follow what is input at the input. That means it is just waits for one clock pulse, and what was sent at the input is reflected at the next state. That is why we are saying that input D is 0, the next state is 0. Input D is 1, the next state is at 1. So that is how, or that is the characteristic table of the D flip-flop. We now look at the excitation table of the D flip-flop, and we do it the same way we do it for the others, but without necessarily really spending too much time. We ask ourselves, if we have the present state and the next state, what is the required input? D. So this is our Qn, this is our Qn plus 1, and they can always make the transitions like we have met before. And we are saying that for us to find the next state is 0, as we have seen in the characteristic table, we require D to be 0. For us to move to 1, we require D to be 1. It is simply following. The next state is always following the D, and therefore we can say that the next state will always be the same as D. So this will be 0, and this is 1. That is the excitation table of the D flip-flop. Of course, you can see this is what is presented here. The state diagram now takes the form of what we have already done. We simply observe that we have two states, 0 and state 1. The state might make such transitions, or it might remain at the same state as it was in. And what do we say? We remain at 0 when D is 0. We transition to 1 when D is 1. We transition to 0 when D is at 0. And we remain at 1 when D is at 1. Quite simplistic. It's easy to figure out. And as you can see, that is what we have right here. So a similar example is asking for sketch the output signal at Q2 for 5 clock periods, and we are told that the flip-flops are initially cleared. You would again draw the table like we have drawn before, and simply follow the examples that we have done for the JK flip-flop and SR, I will not necessarily spend time doing this because we have done it before. All I will mention here is that for such an example, or we will see when you do it, you will see that the output at Q2 will make the following transition. Q2 will move from 0 to 1 to 0 to 1 to 0 to 1 and to 0 again. So this is the first, second and sixth clock pulse that becomes the output waveform or the output at Q2. And you can also draw the waveform, and I believe that is much possible. So just like we have illustrated how the D flip-flop is formed from JK or SR flip-flops, we can form T flip-flop the similar way, except that we are not taking the input to K with an inverter, but it's just coming the same input as the one that is joining J. And we say that we are able to get a T flip-flop, also called toggle flip-flop. So remember, for D, we had inverted this input, and therefore we were able to eliminate the times when J and K are the same. But for the T flip-flop, what we do is when we set the input to J and K as the same, that means that signal is not inverted. What we end up with is we cancel this possibility and this possibility, and we say that J will be the same with K either at 0 or at 1, and therefore we say that and this now becomes our T, and therefore when T is 0, the next state will remain as it was, but when T is 1, the next state will be opposite of the previous state. That is what it is called toggle. It is like it's being toggled depending on the input. So the characteristic table as I have developed is simply this, that when T is 0, the next state is going to be same as the present state, whereas it's going to be opposite of the present state when the input is a 1. And that is the end.